given as this form, where this term calculate using this equation, and this is the start value. This formula calculates the exponent for all primes exclusive prime number 2. Here we define these terms to use in the lemmas, corollaries, proposition, and of course proof of theorem 4.2. Here we have more. Here we have lemmas. We will use lemma 4.8 directly in the proof of proposition 4.1. Here we have corollaries. We will use corollary 4.5 directly in the proof of proposition 4.1. And other lemmas and corollaries we use to get the corollary 4.5 and lemma 4.8. Proposition 4.1 describes the value of AWK, where AWK is the number of multiples of P power K among the factors of our special case. We use induction method to prove proposition 4.1. Based on rational of Legender's formula, we get this formula, and based on proposition 4.1, we get this formula, where this term calculate using this equation, and this is the start value. This is a Python program to verify theorem 4.2. This Python program takes the variables m, h, and w, find all primes number less than or equal to mh, except for 2, calculate the exponent for each prime number that we found. Finally, plot a graph to represent the solutions. This is the script of Python program. Here we have example using Python program. We put this value for our variables, and the Python program calculate 2 power mh and find these primes in the limited. Using Python program, we get this exponent for the primes, and this is the graph of solutions. This is the second bending that we will present, calculation of the exponent of the prime number factor in product of a sequence. We formulate theorem 4.2 to achieving objective 2. The exponent of the prime number p factor in the product of a sequence given by this formula, where this symbol is the exponent of prime number p factor in the product of a sequence. Here we define these terms to use in the lemmas and proof of theorem 5.2. Here we have lemmas, and we will use lemma 5.3 directly in the proof of theorem 5.2. Based on the rational of Legender's formula, we get this formula, and based on lemma 5.3, we get this formula, and using summation, we get this formula, or infinity. But when the summation is limited by this term, we get this formula, and using summation, we get this limited formula. This is a Python program to verify theorem 5.2. This Python program takes input the range limited a and b, and define mathematical function fx, find all prime numbers is than or equal to max value of fx, calculate the exponent for each prime that we found, and finally plot a graph to represent the solutions. Here we have a script of Python program, and here we have an example using Python program. We put this value for our variables, and the Python program calculate the max value of fx and find these primes. Using Python program, we give this exponent for the primes, and here we have graph for solutions. Conclusion. In theorem 4.2, a recursive formula was developed for computing the exponent of a prime p in the multifactorial, extending Legenda's classical formula, and we created a Python program to solve the new formula, thus achieving objective 1. In theorem 5.2, a generalized formula was established to compute the exponent for arbitrary function fx in natural number, providing the scope of prime exponent analysis, and we created a Python program to solve the new formula, thus achieving objective 2. This study extends Legenda's formula to new mathematical context, depending the understanding of prime exponent in complex factorial and product structures, with application in number theory, cryptography, and computational mathematics. These are the references. These more. That's all, and thank you.
Okay, Hamzah, okay, a good presentation. I just want to know, the result is not new, right? Because people can just generalize the factorial very easily by doing the induction.
Yeah, Legenda's formula already
Yeah.
exists, but I formulate a new
Way
formula.
of doing it. Because actually you can just go straight away from the basic of the general formula, and you can do the induction to get your two n factorial to w by using the induction. Using the basic formula of the general. You can do it straight away without all those lemma actually. It's quite easy.
Yeah, I use the rationale of Legenda's formula in one part, in the end of proof only.
So what are the problems that you can solve by having this type? I mean, do you have any problem like asymptotic type problems? Have you heard of that?
Sorry.
Asymptotic problems or inverse of the Legendre. Have you tried that? The
Sorry?
inverse formula for Legendre. Inverse.
Yes.
Have you done it? Have you tried to look into it? I know that your objective only for the induction.
I don't understand, sorry.
Have you thought of doing the inverse of the Legendre? Inverse.
Inverse?
Problem, yeah.
Yes.
I think that one is even better. No, okay.
What is the classic Legendre form? The classic.
Classical Legenda's formula. This one.
So you do the generalization. So which one is your generalization of this?
This one.
So from this formula, can you get back the classical one?
Yes.
So if yes, we should put the summary mark of this theorem.
So you mean can I use this formula to calculate the classical factorial, right?
No, this is it's more general.
Yeah, you reduce back to the original one.
Yeah.
Yeah.
Should get back the original one for the certain value, maybe for a certain value of.
Just we put W equals
Yeah.
0. So 2 for W equal 1, and so we get
So this put the remark.
a classical factorial.
Give some remark for that.
Remark?
Yeah.
Mention that as a remark. Mention that if we substitute W to 0, then we are going to get the classical factorial.
In the thesis.
Yeah.
Okay.
For every generalization. Okay, we do the 5 then for getting certain values of factorial. You can show the table. From this table you get that graph.
Yes, this the exponent and this times.
So what actually you want to show? What actually you want to show from the graph? Can you explain a little bit? What's the meaning of the graph? What's the meaning of the graph?
The vertical is the exponents and the horizontal is the primes. Here primes and here exponent. For example, 3, 5. So this is 5. Here 3. This is exponent and this is the prime 3.
Yeah, that's graph. We understand that. You plot the graph. So now you get the graph. What does it mean? What does it mean? That when I see the graph, I don't know what is.
Maybe to show the rational of the exponents. If the prime is small, then the exponents will be large. If the prime large, exponent small,
So you have
maybe 0.
So you, in your thesis, you should describe a little bit about that.
The behavior of the
Not only the table, not only the graph. It means that you know something from the graph.
because not many people really go into this area of studies, and they don't know why they want the people studying this part, right? So at least if you can tell about the graph and then all those things, why you study this particular one, not just to extend or generalize the formula, but to see why people are doing it, just to study the behavior of the exponent and the prime numbers. But your presentation is very good.
Thank you.
Don't worry, okay? Just to improve the